Let's compare kinetic energies in a two-particle, one-dimensional collision in different reference frames. So we could have one reference frame in which particle 1 is coming in and particle 2 is moving like that. And in particular, so we can call this the ground frame. And now let's consider the center of mass frame. And in the center of mass frame, let's remind you that when we have two different reference frames, the velocity, we'll call this the ground frame g, in the ground frame is equal to the velocity of the object. We'll actually write it this way, just unprimed, v1. The velocity in the center of mass frame, so this is the velocity in the cm frame, plus the relative velocities between the frames, and that's why that's the velocity of the center of mass. So this was our rule for describing how velocities change in different reference frames. And so we can draw the picture in the center of mass frame, v1 initial prime and v2 initial prime. Now let's compare kinetic energies in these different frames. So we know that the kinetic energy in the center of mass frame is just 1/2 m1 v1 initial squared prime, put the prime there, plus 1/2 2 initial prime squared, kinetic energy in the center of mass frame. How do we calculate the kinetic energy in the lab frame? Well, that's a little bit more complicated, and we'll need a little algebra to start that. So let's put kinetic energy in the ground frame. We know is 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. Now what I have to do is use the law, the velocity relationship. And this is going to take a little bit of algebra. We have m1. I'll write v1 prime plus vcm. And remember that any quantity squared is the dot product, v dot v. So I'm going to dot this with itself, v1 initial prime plus v center of mass. And I have the second term, which looks identical to this first term. I'll write it all the way down here, 1/2 m2 v2 initial prime plus vcm, vector dot scalar dot product of v2 initial prime plus vcm. Now, when you take a dot product, remember there's four terms here. There's v1 prime dot v1 prime, which is just v1 prime squared. There's v center of mass dot v center of mass. So that's v center of mass squared. And then there's the cross term. And because they're identical, there's a factor of 2, and it will be repeated below. So the kinetic energy in the ground frame is 1/2 m1. So we'll take v1I prime dotted with itself. That's v1I prime squared. We have the cross term, which is a factor of 2, which will cancel this. So the cross term is m1. That canceled the factor of 2. v1I prime dot vcm plus the vcm with itself. So that's 1/2 m1 vcm squared. Now I have exactly the same thing on the next one. So we'll write that down, 1/2 v2i prime squared plus m2 v2i prime dot vcm. That's the same in both, plus 1/2 m2 vcm squared. Now, let's look carefully at what we have. We have 1/2 m1 v1 prime squared. This is an m2. 1/2 m2 v2i prime squared. So we have 1/2 m1 v1i prime squared plus 1/2 m2 v2i prime squared. And you're already noticing that's the kinetic energy in the center of mass frame. We have the total mass, 1/2 m1 plus m2 vcm squared. I can just put a little check to show which terms I've done so far. And now here's the interesting one. We have m1 v1 v2i prime plus m2 v2i prime dot vcm. That represents this term and this term added together. But recall that the center of mass reference frame is defined by the condition that the total momentum in that frame is 0. So this term is 0. And thus we get that the kinetic energy in the ground frame is equal to the kinetic energy in the center of mass frame plus 1/2 m1 plus m2 times vcm squared. And that's how kinetic energy is in different reference frames. And the next thing we'll look at is how that changes when we have a collision. Let's calculate the kinetic energy in the center of mass frame of two objects that are colliding. I'm going to use prime for the center of mass frame velocity. So we have v1 prime and we have v2 prime. And recall two things. That when we calculated v1 prime in the center of mass frame, we found that this was equal to the reduced mass divided by m1 times the relative velocities of the two objects, v1 prime minus v2 prime. Now, in the center of mass frame, this quantity is a reference frame independent, and so we can just write that as v12. It's the relative velocity is reference frame independent. So we also knew that v2 prime was equal to minus mu over m2 v12. So now let's calculate the kinetic energy in the center of mass frame. So kcm is 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Now let's use our results in terms of relative velocity. So we have 1/2 m1 mu over m1 times v12 squared, because we're squaring that, plus 1/2 m2 mu. The minus sign doesn't matter anymore because we're squaring it. v2 squared. I could put that in there, it wouldn't matter. And now what we have is we have a half. One of the m1s cancels, so we have a mu squared over m1 v12 squared plus 1/2 another mu squared over m2 times v12 squared. So I pull out the common terms, mu squared, v12 squared. I have 1 over m1 plus 1 over m2. But recall that the reduced mass was precisely 1 over m1 plus 1 over m2. And so I get 1/2 mu times v12 squared is the kinetic energy in the center of mass frame. So what that means is a way of thinking, if this were just a simple reduced mass problem with the relative speed of v12 squared, I can write down the kinetic energy. But that's the kinetic energy in the center of mass frame. And therefore, the change in kinetic energy is, in a collision, is just 1/2 v12 initial final squared minus, and it's the same mu, so we'll just put a parentheses, minus v12 initial squared. And if the collision is elastic, remember our elastic collision showed that v12 initial was minus v12 final. So an elastic collision satisfies that condition, and you can see directly that delta kcm is 0 in that case. And a completely inelastic collision has the two objects moving together at the end, so v12 final is 0, so completely inelastic. . is the condition that V12 final is 0, because the objects stick together. And then we have a very simple result for the change in kinetic energy for completely inelastic collision. It's only negative 1/2 mu V12 initial quantity squared. Now, when we did these calculations, we saw that the kinetic energy in the ground frame was equal to the kinetic energy in the center of mass frame plus a constant term, m1 plus m2 times vcm squared. And this is a constant, whether you're in the initial or the final picture. So if we look at the change in kinetic energy in the ground frame, that's equal to the change in kinetic energy in the center of mass frame, but this term is a constant, so there's no change in that term. And so we have a crucial result that the change in kinetic energy in the ground frame is equal to the change in kinetic energy in the center of mass frame. Now, let's look at an example of a collision that's completely inelastic. So we have object 1, and it's coming in with V1 initial, and object 2, let's make it at rest. And afterwards, object 1 and 2 stick together, and they go off with V final. So here's a collision in an inelastic frame. Now, in the center of mass frame, the two objects, so here's our lab or ground frame. I can call it the lab frame because that one's at rest. And this is the CM frame. And there we have V1 prime and V2 prime. They're both moving. And now, in the center of mass frame, they're at rest at the end of the collision. So in this collision, we can analyze it. And now what I want to show is that the change in kinetic energy, recall from our previous calculation that the kinetic energy in the center of mass frame was equal to 1/2 mu times the relative velocity squared. So remember, V12 was equal to V1 minus V2. And so the change in kinetic energy in the center of mass frame is the final kinetic energy is 0 minus 1/2 the kinetic energy in the initial state. And what is this quantity, initial? Well, this was a reference frame independent concept, so we can just look at the lab frame and write this as V1 initial I hat, where that's I hat because this object is at rest. And so right away, we have that the change in kinetic energy is minus 1/2. Now remember, mu was m1, m2 over m1 plus m2 times V1 initial squared. And that's the same change in kinetic energy as the ground frame. So by using our result here and our result there, we were able to very quickly assess how much kinetic energy is lost in this inelastic collision. And where does that kinetic energy go? It can go to a variety of places. Deformation of objects. It can go into sound. It can go into thermal energy that gets re-radiated, that is transmitted into the environment through, diffuses into the environment. However, that's how much is changed.